The goal of section 9.3 is to understand the relationship between a sequence and a series. We have learned that the value of a series is equal to the limit of the sequence of partial sums. We will now apply these concepts to a specific example, the geometric series. We have already briefly examined the geometric sequence. Let's review that for just a minute. This can be expressed as the sequence a times r to the nth power from n equals 0 to infinity. Remember, a sequence is a pattern of numbers or a set of numbers that follows a specific pattern. So we're just looking at a set of numbers here. Let's compare this to the geometric series. Remember, a geometric series is the sum of the geometric sequence. This is going to look like a plus ar plus ar squared plus ar cubed, much like a polynomial looks. So where the sequence is simply the set of numbers following this pattern, the series is the sum of those numbers. The use of the subscript or the index n for the sequence and the index k for the series is just customary. You can actually use any index in either place. The very best thing about recognizing a geometric series is that it is very easy to sum. We will determine the value of a geometric series as the limit of the sequence of partial sums. So let's begin with finite sums. The nth partial sum of a geometric series is given by s sub n equals a times 1 minus r to the nth power divided by 1 minus r. Now there's a few hidden nuances about this formula that are very important to recognize. So we're going to develop the proof so we understand how this formula works. We will begin by defining the nth partial sum of this geometric series. We'll say let s sub n equal the sum from k equals 0. Now check out my upper limit. I'm going to set it at n minus 1. That'll be a very important detail to keep up with, of a times r to the k. Now, if we begin expanding this particular formula, plugging in first of all the index k equals 0, the first term is a. If k equals 1, the second term is a times r. Then we would have a times r squared plus, and we would continue this until we get to our upper limit of summation, which we have defined as n minus 1. So this is the expanded form of our nth partial sum. Now, I'm going to go ahead and multiply both sides by r. So we have r times s sub n equals ar plus ar squared plus ar cubed. This is going to continue until we get to our last term. If we multiply that one by r, we're going to have a times r to the nth power. If we subtract the second equation from the first, that is, we subtract every like term from the second equation from the first, we're going to end up with an equation for which we can solve for the nth partial sum. So we have s sub n minus r times s sub n. Notice a would remain after the subtraction, but we'll have a lot of like terms that cancel. In fact, they cancel in this diagonal pattern. So this term would cancel with whatever term would live right here. This term is going to cancel with the term that precedes this last one. So the only thing that's left on this last line is minus ar to the nth power. Now we are attempting to determine a formula for the nth partial sum. It's represented by s sub n. Notice I have it in these two places in the equation. So I'm going to algebraically solve for s sub n. Factoring it out as a GCF, that leaves behind 1 minus r. And while we're at it, let's factor out our GCF on the right side, which is a. Then we can divide both sides by 1 minus r, and we have the formula for the nth partial sum of a geometric series. And this, of course, matches the formula that was listed at the top. However, there is one very subtle and important detail that you need to know. Recall that when we derived this formula, the lower limit of summation was 0 and the upper limit of summation was n minus 1. And the sum we obtained is a times 1 minus r to the nth power over 1 minus r. It's very important that when I apply this formula, all of the details line up. That is, this formula will not work unless my lower limit of summation is 0. Also notice that the n that I'm using in the formula is actually 1 greater than my upper limit of summation. So let's go ahead and apply this formula in example 3. Evaluate the geometric sums. First of all, we're going to find the sum from k equals 0 to 8 of 3 to the k. Notice I have a constant base and I've got my index in the exponent, so this is a geometric series. Also notice the important detail that the lower limit of summation here is 0. So this is going to be equal to a, which in this case is 1. R, of course, is the base of my exponential expression there. A times 1 minus r, which is 3, to the nth power. But remember, n is 1 greater than my upper limit of summation. So we have 1 minus 3 to the 9th power over 1 minus 3. If we plug in 3 to the 9th on our calculator, we're going to get 19,683. And in the denominator, we have a negative 2. So our nth partial sum then is 9,841. Notice what this particular formula does. We have simply added the first 8 terms, 9 terms total, of this particular series and shortcutted it with the formula to end up with 9841. Another way of actually thinking about this particular problem is just to expand the series. So what we're actually doing here, the sum from k equals 0 to 8 of 3 to the k, we're evaluating 3 to the 0th plus 3 to the 1st plus 3 squared plus 3 cubed plus 3 to the 4th, 3 to the 5th. I'm going to continue here on the next line, plus 3 to the 6th, plus 3 to the 7th, plus 3 to the 8th. If we type that into our calculator and evaluate the result, we would find out it's 9841. So the formula that we are examining is allowing us to shortcut this tedious work based on the pattern and quickly obtain the sum. Let's practice the same formula on the next example. We have the sum from k equals 4 to 12 of 2 to the k. Because of my exponential expression here, we know this is a geometric series, so this formula applies. But notice my lower limit of summation here is 4, not 0. In order for our formula to work, the lower limit of summation must be 0. So I need to rewrite this series starting with the lower index of 0. Notice I'm subtracting 4 from this index. Whatever I do to the lower index, I must also do to the upper limit of summation. So 12 minus 4 gives me 8. Now, I can't just make those changes arbitrarily. As you know, we have to balance it out somewhere else. So if I decrease my index over here by 4, then I need to increase this index by 4. That way, those two changes balance out. If we expand both of these expressions, they would generate exactly the same sum. For example, let's just take the first term. The first term on the left here would be 2 to the 4th power. The first term over here on the right, if we plug in k equals 0, we would have 2 to the 0th plus 4 or 2 to the 4th. So both of these series are equivalent, but the second expression is now in better alignment to apply our formula. The next thing we want to strive for is making our formula look just like this. So I'm going to split up this exponential expression. Let's call it 2 to the 4th times 2 to the k power. So first of all, I'm switching the order of these two exponents, and then we know that when we're multiplying like bases, we add the exponents. So I'm simply applying that rule in reverse. Since we're adding the exponents, we can rewrite this as a product of like bases. So we have the sum from k equals 0 to 8 of 2 to the 4th, which is 16, times 2 to the k power. Now that this particular series matches the pattern of our formula, we can now apply the formula for the sum. So we're going to have a, our coefficient here is 16, times 1 minus r, which is 2, to the exponent 9. Remember, 9 is 1 more than our upper limit of summation here, over 1 minus r. 2 to the 9th power is 512 from our calculator. Looks like we have 16 times negative 511 over negative 1, or 8,176. So this would be the sum of 9 terms, starting from 0, stopping at the 8th term, so a total of 9 terms. If I were to expand that, it would give me the same value as our shortcut formula. So the point of this particular problem is just to remind you to watch the details. The lower limit of summation has to be 0, and this must match the formula exactly in order to apply the formula for the sum. Also remember that the value that I plug in here is 1 more than the upper limit of summation, 1. Now consider example C. 1 plus 2/3 plus 4/9 plus 8 over 27. Of course, one way to evaluate that is simply to sum those numbers. And you could certainly start with that, but let's look at how this connects to a geometric series, a finite geometric series. Notice this could be written as the sum from k equals 0 to 3 of 2/3 to the k power. What I'm recognizing is that from one term to the next, we're multiplying by that common ratio of 2/3. Also, if we treat the first term as not the first term but the 0th term, then we're starting from k equals 0 and we're looking at stopping at k equals 3. So this is definitely a finite geometric series. So if we apply our formula, we're going to have a times 1 minus r raised to the nth power. Remember, that's 1 greater than our upper limit of summation, over 1 minus 2/3. Evaluating our exponent here, we have 1 minus 16 over 81, and in the denominator we have 1/3. Working out our arithmetic here, we have 65 over 81 divided by 1/3, and we can cure that complex fraction by multiplying the top and the bottom by 3. For a final result of 65 over 27, which of course you will obtain if you check this by simply adding those 4 fractions together. But again, once you understand how to express this as a geometric series, if you see a similar problem but it is an infinite sum, now you'll know how to convert it at least to a geometric series. Having said that, it is time to progress from finite sums to infinite sums. Believe it or not, the sum of an infinite geometric series has a formula that's even simpler than the formula for the sum of a finite geometric series. The sum of the geometric series is given by k equals 0 to infinity of ar to the k equals a over 1 minus r. Now this series will only converge if the ratio, the absolute value of r, is less than 1. Now, previously we learned that the sum of an infinite series is equal to the limit of the sequence of finite sums. So for our particular geometric series, we need to find the limit as n approaches infinity of the sequence of finite sums. And all we have to do here is plug in the formula that we previously derived. So the nth partial sum of a geometric series looks something like this. As n goes to infinity, this term right here will go to 0 only if The absolute value of r is less than 1. So if r is less than 1, then the sum of an infinite geometric series is a times 1, or just a, over 1 minus r. Again, it's very important to stress this is provided that the absolute value of our ratio is less than 1. The simplicity of this formula is really amazing to me. So let's see how it applies to the following geometric series. We want to find the sum from j equals 0 to infinity of 1 over pi to the j. Now remember, we can use any index. That just helps us to keep up with the particular position of the term in the sequence or series. So because we begin counting at j equals 0 and we're looking at an infinite sum, we can apply our formula a over 1 minus r. It is that easy to find the sum of an infinite geometric series. So to simplify this, I'm going to go ahead and multiply the top and the bottom by pi, and we'll distribute in the denominator to obtain pi over pi minus 1. So the exact sum of our infinite geometric series is pi over pi minus 1. If you compare this process of summing an infinite geometric series to the process we went through in the very first section, 9.3.1, where we had to find the limit of a sequence of partial sums, that required a ton of effort. But keep in mind, we've already done that effort in general. We found the nth term formula for the sequence of partial sums, then we evaluated the limit of that value, and we ended up with that very simple formula. So we've been through the process in general, so in application it makes our life pretty easy. Let's see how this applies on example B. Notice in this case we have the sum from k equals 1 to infinity of something that doesn't really look like the geometric series at first. So what we're going to do is manipulate this until it is resembling the geometric series. We know that to apply our formulas, the lower limit of summation must be 0. So if I decrease the index by 1 in the position of these placeholders, then I have to increase these k's by 1. So we're going to end up with 3 to the k over 4 to the k plus 2. So once again, we decreased this index by 1, and to counterbalance that, we increased these by 1. Now let's go ahead and split up that exponential in the denominator. We could rewrite this as 3 to the k. I'm going to switch positions here. 4 squared times 4 to the k, or the sum from k equals 0 to infinity of 1/16 times 3/4 to the k. So this 4 squared in the denominator yields this 1/16. Then the 3 over 4, they share the same exponent, so I can group those together as a quotient and raise the entire quotient to the kth power. This tells us that a is 16 and r is 3/4. Since r is less than 1, then this series will converge. And we can determine what it converges to. We evaluate a over 1 minus r. So working out our arithmetic, we have 1/16 over 1/4. Going to multiply the top and the bottom by 4 over 1 and reduce. So our sum then is 1/4. Let's look at example C. We have the sum from I equals 2 to infinity of 5/2 to the I. Now the first thing that may catch your eye is that our lower index of summation here is not 0. However, it doesn't matter on this one. Notice that our ratio, 5/2, is greater than 1. If that ratio is greater than 1, then the series diverges. That is, if I keep adding those terms together, the sum is going to get larger and larger and larger, and it's never going to settle down around a finite value. If you did not notice that at first and you attempted to apply the formula, you'd end up with a negative sum, which is absurd for adding an infinite number of positive terms. So it may catch your attention at that point. But the simple test is that if r is greater than 1, the series diverges. No need to apply the formula. Example D is also a little bit different. Notice in this case, the ratio is negative. The absolute value of that ratio, however, is less than 1, so the formula applies. Also, check that lower index of summation. It is 0, so we are good to go to apply our formula. So we have A over 1 minus r. R happens to be a negative number, but that's no big deal. We can plug it in directly. So in the denominator, we have 1 plus 9/10, or when we evaluate that, we would have 19 over 10, and simplifying our complex fraction, we'd have a sum of 10/19. The interesting thing about this geometric series is that as n alternates from even to odd, the sign of the term changes from positive to negative. However, our sum came out to be a positive value. As long as the value of r is less than 1, then 1 minus a number less than 1 will always be a positive value. So we'll end up with a positive sum for geometric series that converge. Geometric series are incredibly common and useful in all kinds of applications. We'll look at two examples of applications. The first one is simply dealing with number theory, and the second one is a real-life application in medicine. Example 5, express 5.1283 repeating as the ratio of two integers. Because this value is written as a repeating decimal, then we know that it can be expressed as a rational number or the ratio of two integers. So we're going to expand this in the form of a geometric series and use our new formula to write it as the ratio of two integers. So let's take our number 5.1283 repeating and really get an understanding of what this number is. All of our infinite decimals can be written as the sum of finite decimals. So I'm going to take that 5.12 off and express this as the sum of a repeating pattern here. The only part of this sum that really stands apart as being different is that 5.12. So we will separate that part away and we'll express the rest as a geometric series. We want to start counting from 0 and express this as an infinite pattern. So this will be our 0th term, this will be our first term, second term, so on and so forth. If we write that first or that 0th term as a fraction, we could express it as 83 over 10,000, and I'm just using place value there. Then notice as we go from term to term, we're moving the decimal to the left 2 places. That's equivalent to multiplying by 1/100th. So from the first term to the second term, we multiply by 100th. If we go from this term to this term, we've done it twice. So we're just going to express this as an exponent of k. So isn't it interesting to review this repeating decimal now as a geometric series? Because our ratio r, 1/100th, is less than 1, we can go ahead and apply our formula for the sum of an infinite geometric series. We have our a term over 1 minus r, or 5.12 plus 83 over 10,000. Notice in the denominator we would end up with 99 over 100. Since we're dividing by a fraction, we're going to end up multiplying by the reciprocal. So I'm skipping a couple of steps here. Remember, you can always verify that arithmetic with your calculator. So we have 5.12 plus 83 over 9,900. Now for this part, I actually am going to use my calculator, type it in, convert it to a fraction. 5.12 plus 83 over 9,900 gives me 50,771 divided by 9,900. So we have taken our infinite repeating decimal and expressed it as the ratio of two integers. To check this, you can take the top number divided by the bottom number on your calculator and you will see this decimal expansion. So this example shows you how to apply the formula for the sum of an infinite geometric series, but also a new way of viewing those repeating decimals. So note if I expand this geometric series, I'm going to have 200 plus 100 plus 50 plus 25, so on and so forth. So at least at this point we can see our fourth partial sum developed, which is what we had right here. But we don't have to go that far. We can recognize this is an infinite geometric series with the sum of a over 1 minus r. That's 200 over 1/2. 200 divided by 1/2 is 400 milligrams. So the steady state amount of the antibiotic in our blood over time, even though we keep taking 200 milligrams every 6 hours, is a maximum value of 400 milligrams. Very interesting that that can be modeled with a geometric series.